Hey guys, welcome back to another Newtonian gravitation problem. Earth's gravitational field strength at the surface is 9.80 newtons per kilogram. Determine the distance as a multiple of Earth's radius, RE, above Earth's surface, at which the magnitude of the acceleration due to gravity is 3.25 newtons per kilogram. So essentially it's becoming almost a third of what it is. So the way to do this, we're not given any distances. We're told to give the distance relative to Earth's radius. Okay, so we want to see the point at which the acceleration due to gravity changes. So let's first come up with an expression for the acceleration due to gravity. Now, similar things to this were covered in video 143, Newtonian Gravitation 1. But to quickly go over what was done in that video, universal law of gravitation looks like this. You've got your force of gravity equal to your gravitational constant, mass 1, mass 2, over the distance between their centers squared. Now, on Earth, the equation becomes much simpler, right? We just say that Fg is equal to mg. Okay, so let's say that in this original formula, we use this one on Earth. Then mass 1 would be the mass of the Earth, and mass 2 would be the mass of the other object. Okay, so in this case, like a satellite. Okay, so we can say that Fg on Earth would be equal to m2g because the g already takes into account the mass of the Earth, the distance between their centers, and the gravitational constant. So by looking at the two formulas like this, you can see that g, the acceleration due to gravity, is essentially the universal gravitational constant times the large mass causing this acceleration divided by the distance between their centers squared. So we can say that g is equal to gm1 over r squared. So m1 is the mass of the Earth. You can do this for any object, obviously, in space. In this particular example, m1 would be the mass of the Earth. Now, because we're looking for the distance as a multiple of Earth's radius, we're not given Earth's radius, and you're not supposed to actually plug it in because the question actually says determine it as a multiple of Earth's radius. So we're going to have to solve this as a ratio. And the way that we're going to do that is compare the accelerations due to gravity on Earth versus at this certain distance, because we have an expression for the acceleration due to gravity now. Okay, so this ratio is going to be the acceleration due to gravity on Earth over the acceleration due to gravity at some distance d. Okay, so let's plug it in. Gm over r squared over gm over r squared. Now, the g's are the same for both. The masses are the same for both because it's still mass of the Earth causing the acceleration. So you can put the subscript e if you'd like. The distances are what are going to be different. For the acceleration due to gravity on Earth, this is the distance between the center of the Earth and the surface, the radius. And this will be rd. Okay, this is going to be the distance between the center of the Earth and this new location. That's what we're trying to find. So there's a couple things we can cancel out here. We can cancel out g because it's the same. We can also cancel out mass of the Earth because it's the same. Now, hopefully you can see based on this fraction, because you have a denominator in the denominator, if you were to bring this up to the numerator, you would have to flip it. In other words, the rd squared comes up on top of the re squared. Okay, so essentially with this you're getting ge over gd equals rd squared over re squared. Now here's the fun part. We know what ge is, we know what gd is. We're given those in the question. Okay, so all that's left are these two things, which are exactly what we need for our final expression. So ge is 9.80 newtons per kilogram. gd is 3.25 newtons per kilogram. So that's equal to rd squared over re squared. Okay, so the beautiful thing is that our formulas, our units, cancel out here. Newtons per kilogram, which is exactly what you want when you have a ratio. You just want two numbers given relative to each other. Now, we're trying to come up with an expression for rd, so we're going to take the re and multiply it across. And so we're going to get rd squared is equal to re squared times this quotient, right? So this quotient turns out to be 3.02. Okay, so we're almost there. We just have to take the square root of both sides because I need to get rd by itself. So square root that. Make sure you square root both of those. And of course, RD squared square rooted is going to be RD. On this side, RE squared is going to be RE. And you just have to take the square root of 3.02. You're going to get 1.74. Okay, in other words, this is the distance from the center of the Earth, right? 1.74 RE. The question says, determine the distance above Earth's surface, right? So here's the thing. If you've got the Earth and you've got the satellite, we know that this full distance here, this total distance is 1.74 RE. But you also know that this distance in here is just RE. So to find the difference, this distance here, it's simply going to be, well, this is RD now, right? This is the new RD. Okay, the distance above Earth's surface is simply 1.74 RE minus RE. And as you would see in mathematics, there's an invisible one here. 1.74 minus 1 is 0.74. So the distance above Earth's surface for the satellite is 0.74 RE, or 74% of the radius of the Earth. And that's it for the video, guys. Be sure to smash that like button if you enjoyed it, so that I know what I'm doing makes sense to you guys. It's a good way for me to see. And also be sure to subscribe to Physics in the Flesh so you're always alerted of the latest videos I post every weekday at 12 noon. Stay tuned tomorrow for 145, Newtonian Gravitation 3. Alright guys, that's it for this video. I hope you enjoyed it. If you did, be sure to smash that like button so I know what I'm doing makes sense to you guys. And you know how you can stay tuned for my latest videos? By subscribing to Physics in the Flesh. I post every weekday at 12 noon, and this way you guys can always be the first to know when I post a new video. As always, guys, thank you so much for watching. If you missed any of my earlier videos, be sure to click over there on the right. You can click and watch those videos on your screen right now. Anyways, guys, Physics in the Flesh out. Whoop, whoop. Holy crap, my nose looks big on camera.